intelligence today, which is not yet a standard in ORAN, but we are definitely pushing for it. So we'll be talking about our platform, which is EdgeRIC, which is for delivering real-time control to the radio access network. And by real-time, we actually mean sub-millisecond or more at the level of microsecond latency and control to the radio access network. This work is a joint collaboration between UC San Diego and the Texas A&M University, and we've also had like a very successful collaboration with the OAIC team in recently submitting one paper with them. So EdgeRIC overview. So we till now we've looked at all the RICs that are hosted in the cloud. We have looked at non-real-time RICs where all the R apps are hosted. Non-real-time RICs meaning having operating at a time scale of beyond 1 second. Then we also have the near real-time RICs. The session today morning talked about X apps, which is operating at timescales beyond 50 milliseconds to 1 second. Both these RICs are kind of hosted in the cloud, much beyond the central units, and everybody talked about the E2 interface, which is for collecting all the metrics from the radio access network, taking it to the cloud, and doing some decision and telling the RAN what kind of policy or decisions to act on. So these kinds of RICs today are really good for any kind of network reconfigurations in the cloud. Example use cases can be about like traffic steering, then network slicing, how much resources to allocate to a particular site, and so on, which is like very macro level network optimizations. But today, what we'll be looking at right now would be like really fine-grained control to the radio access network. That is all the functionalities that actually go on in the distributed units, which is basically the PHY, MAC, and the RLC, which operates at the granularity of every slot, or the TTI, which is sub-millisecond basically. And that's where we talk about co-locating our RIC, the real-time RIC or EdgeRIC, with the DU distributed unit. And all the apps running on EdgeRIC need to operate at the microsecond timescale. We call it micro apps for now, or D apps, more commonly known. So the main idea of EdgeRIC is to kind of integrate some kind of application aware also in its decision making to all the PHY and MAC layer functionalities. So as of today, I don't think there is any optimizations in place for the lower layer RAN functions, which is like the DU, all the functions which are located at the distributed units. And by PHY and MAC functionalities, I mean like various controls like resource block scheduling, MCS selection, and various other network functionalities at the 1 millisecond time scale. So what we are basically looking at is 5G talks about these frames and slots, and a frame at best is 1 millisecond subframe where a lot of network decisions happen. And what we are trying to actually focus on is the intelligence for decision making for each of these slots. What kind of decisions need to be taken for each of these slots? That's where EdgeRIC comes into play. So going over the EdgeRIC architecture, our code base is also based on the SRS RAN network. The network is completely written in C++, where we have integrated our own RT-E2 agent in the SRS RAN code base, which sits in the radio access network. The way we have developed the architecture is that every TTI, the RAN publishes the metrics pertaining to that particular slot or the transmission time interval. We defined our own interface called the RT-E2. This is the real-time E2 interface. We call it the RT-E2 report message, which carries all the TTI level metrics from the RAN to our EdgeRIC, and where EdgeRIC subscribes to these information and through a function defined by get_metrics, and then we have EdgeRIC computes some decision on the metrics received, and sends its control. It publishes the control over the RT-E2 policy, that is what decision to be taken for the next TTI, and which is then subscribed to by the radio access network to actually act on that decision. Now, one important metric that we need to send to, which allows this real-time nature, is basically the RAN index and the RIC index. It is very essential to maintain this TTI by TTI sync to attain the real-time nature. That is, I send you metrics for this. The EdgeRIC also tells RAN that this is a decision pertaining to this particular TTI. Otherwise, it's of not much use. So there's a default mechanism in the RAN. In case it does not receive the TTI decision, it will just default back to its own policy. So it is basically EdgeRIC is supposed to deliver like best effort real-time intelligence. So main intelligence on EdgeRIC is to maintain this TTI by TTI sync by always ensuring that RAN index is equal to RIC index so that the state and action is always correlated with each other. So the most important takeaway for delivering any kind of real-time control is to maintain that my state and action is TTI by TTI synced. Otherwise, we just let it go. So talking about the RTE2 report message, what does it look like? Basically, it contains, as of now, this is what our code base supports, a set of metrics for per UE. That is, we consist of the CQI, the backlog buffer, SNR, the uplink buffer, the amount of transmitted bytes and the amount of received bytes on a per UE basis at per TTI. And the UE underscore data is kind of repeated for each of the UEs that are running in the network. And finally, we also have the RIC ID and the RAN ID. This is compiled into a protobuf message, which is Google's protocol buffers of code base. And the reason, so it is very similar to text-based formats, which is like JSON and XML, but those are text-based, which means it requires a very high data rate. But protobuf basically compiles this entire information, this entire schema into bits or binary formats, which reduces the amount of communication which is needed between the RAN and EdgeRIC. And that's what basically the protobuf schema looks like, which is also compiled into the SRS RAN code base. Similarly, talking about the communication between EdgeRIC to RAN, we have the RTE2 policy. So what does the structure of the message look like? It's basically you have each of these micro apps which will contain these messages, the control message. What does each message format look like? Each control message contains the UE's RNTI, which is the identifier for that particular UE, and then the action specific to that UE, like how to react to that UE at that particular TTI, and so on. Again, we have corresponding the protobuf schema, which is deciding the policy report message. And next on, this is the entire architecture picture that we have in place. EdgeRIC also has an in-memory database. We use Redis database for EdgeRIC's for storing all of the metrics that EdgeRIC receives. Micro apps, how does micro apps work? So it pulls all the metrics from the EdgeRIC database with this get metrics function. It computes some policy based on the metrics it receives, and it sends a control out to the EdgeRIC messenger, which then publishes it to the RAN. So this is every TTI we are experiencing this process going on. So that was a brief overview of EdgeRIC. I think we will move on to pulling the EdgeRIC environment Docker image into the demo part of our section. We have Woohyun, Ish, and Bhavya who can help with the if anybody runs into any issues. So I'll be looking at the documentation. I think it's already online with the OAIC GitHub page, the docs. So we can do it one by one. Yeah. So what we provide here is basically the Docker container of this entire environment, which has our version of SRS RAN with EdgeRIC and all the dependencies required, like protobuf and all the Python dependencies as well, when that is required to run all the ML algorithms that we'll be deploying for real-time control. So we'll first move ahead with pulling the image. The first step, yeah, we can do it step by step. Yeah, sure. Sorry. Mm-hmm. What does it live? Does it live at the DU set, DU level? Yeah, it is meant to offer decisions to the DU functions. So EdgeRIC is something which is co-located with the DU compute. Yes.
But does it have an the equivalent E connection?
E2? Yeah. So what I mentioned was the RT-E2 connection. So the RT-E2 interface is what we are defining for the real-time interface for communication between the RAN and RIC.
So it is a new proposed.
So this is not part of the set.
No, because in standard we go only up to near real time, and they are proposing doing better than what we have. But it is real time now, so we can do below 1 millisecond processing. So that's the proposal.
Yeah, so we'll provide the Docker container. Let's move ahead with first cloning the Git repo, our Git repo. So, okay. Yeah, please let me know. Sorry. Okay. Okay, once we clone it, let's just get inside the repository that we just cloned. That is the command out here. So make sure that you're on this branch, which is the OAIC workshop for this particular tutorial. Okay. So now we'll move ahead and pull this Docker container, which is the entire containerized version of our code base. Just go ahead and pull. It is available on Docker Hub, this entire image of our okay, yeah, this might take some time. So in between, I could go over what we are to expect today from this tutorial. First thing is I can go over how to write these micro apps.
Who is still downloading? Anyone still on? Yes, please.
Yeah, it's downloading, right? So I can, yeah.
Oh.
Okay, so the download may happen in the background. You don't need to have download finished to listen.
Yeah, so please start.
Okay. So how to write micro apps? It's pretty straightforward. The EdgeRIC part of the code base is entirely written on Python. It is interfaced with the OpenAI and OpenAI Gymnasium interface, so you can run any kind of feedback-based policies like reinforcement learning algorithms. All you have to do is basically first import the EdgeRIC messenger class, which is also defined as part of our EdgeRIC code base. All of this side that I'm talking about is completely written in Python. Then this function get underscore metrics is belongs to the EdgeRIC messenger class. So this is used to actually retrieve all the RAN state from the radio access network. This is called every TTI. So every TTI meaning every 1 millisecond or every slot. It is supposed to receive the network metrics. Then you compute your policy. You have the network metrics. Now you compute your policy corresponding to each UE. That is, for each UE, what should be the action taken. Here we are showing a simple scheduling algorithm where we are trying to decide what is the number of resource block groups that should be allocated to each UE for the next time slot. And once you compute your custom policy or you get your custom decision, you simply publish this to the EdgeRIC messenger, which is responsible to send it over to the radio access network to take action for the next TTI. What we will run here today is an example micro app, which is a Mac level scheduler. It sits at the MAC functionality and it is responsible for scheduling decisions every TTI. By scheduling decisions, I mean the total number of physical resource block groups that need to be allocated to each of the UEs, depending on what kind of traffic they are running, what is their underlying channel state, and so on. So again, we have the radio access network sitting with our RTE2 agent. We have multiple UEs that will be connected to this network. Each will have different requirements. That's the most important thing. They will be running different types of traffic and they will be under different types of wireless channel conditions. So all of this, so the question is, how do I prioritize these users, or based on the priority, how many resource block groups should I actually allocate to the users for this particular slot? So you have EdgeRIC, which receives the network state in real time, and it sends back a weight, which is WI for each UE. What is WI? It's basically the fraction of PRBs that it is supposed to be allocated. So we send WI because we modify the SRS rank code base to allow for this weight based abstraction of the scheduling control, because the number of PRBs available to be scheduled every TTI is never the same, because some TTIs require some of the PRBs to be used for control messages, whereas for other TTIs you have the entire resource block available for use. So by abstracting these with weights, we just act on the fraction of the total available PRBs uh, that is ready to be scheduled for that particular TTI. So one advantage with this weight-based scheduling is you can basically do any kind of scheduling policy by setting a weight like round robin. You just set the weight for that UE to be 1 and all others get 0. And that means that for that particular TTI, only one UE gets scheduled and so on. So any kind of scheduling algorithm can be abstracted with with these weights. So I am hoping that the image has been downloaded so that we can move on to the installation part of it. Okay, yeah, just let me know if once, yeah. Okay, I downloaded it already, so. So we'll go over various algorithms and we will see how each of these algorithms actually perform in providing the total system throughput. Um, yeah, that's okay. That's okay. So as long as you see this line here downloaded and everything, I think you're good to go. Yeah. 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 I mean, we just want to operate at the microsecond time scale. So. Sorry? So the protocol, the protobuf, which is like Google's compiler, that is actually a compression-based algorithm to actually compress that entire data in text to bits. Yeah, so the protobuf is a protocol that does this compression. Yeah. 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 So the entire round trip time should be 1 millisecond. Lesser. Yeah. So it depends. You're supposed to be reacting to every slot. So that's why I want to keep it to every slot, not really 1 millisecond. The idea is to impart intelligence every slot. Mm-hmm. Yeah. So sending data and receiving that back data, the entire round trip time, for like we sent a data for almost 100 UEs. The communication is not very high. It's less than 50 microseconds, sending and receiving data. Apart from the system side of things, there's also a lot of research to be done on ML model customizations or the policy you are computing to ensure that your policy actually computes in less than 200 or 300 microseconds. That is the time gap that you have for which the slot operates. So that is ML-based research. We've done some optimizations as well on that end to actually do the inference in less than 300 microseconds. Shall we move ahead? Okay. Let's start up the Docker container, which is this command out here. This should take you inside the Docker container, and you should be, so this green thing should become white. That is a good indicator that you're inside the Docker container now. Once you are inside the Docker container, you can run all commands without the sudo mode. Let's just move ahead and start building the SRS run by running this command out here, make_ran.sh. Yeah, we need like 10 or 12 terminals, I think. Yeah. Yeah. So I hope everyone started with the build process, right? Okay. Okay. Oh, you're still pulling the image? Okay. So I could, in the meantime, I would like to go over what our build exactly looks like. So if everyone's running this build process, I could go over some slides in between. Is that okay with everyone? Cool. Yeah, so while the installation happens, let's talk about like some key areas that EdgeRIC supports, application aware RAN optimization, which we'll see in the demo, like how scheduling, like different policies affect scheduling and the total supported system throughput. We have security and privacy. My colleague Ish presented his Beam Armor project, which was also done with EdgeRIC, and he'll also talk about some energy optimization stuff we've been looking at, and some AI to actually deliver next generation applications. We will see this in the later part of the talk, but just wanted to bring it up front. What are the key areas that we are actually looking at with real-time intelligence? So what does our build basically look like? Till up until now, we have been running the entire SRS RAN network with these virtual radios over GNU radio blocks and the ZMQ source and sync, ZMQ source and sync, basically taking the IQ samples out from the SRS ENB, transporting it over the GRC broker to the different UEs. I guess we did this yesterday as well as today in the session, in the morning session. The additional change in our code base, we wanted to incorporate some channel into our SRS UE. So our SRS UE is basically a modified version of the SRS code base provided. We incorporate hooks to read the CQI from a trace file basically. The trace file is basically real world data collected from real world measurements. So every time the UE code base runs, the CQI is basically read from the trace file every TTI. So we incorporate this channel into our code base to kind of account for the changing wireless conditions. Channel trace driven network bring up. So we support a lot of different mobility scenarios. We can simply go on a drive test and collect a lot of traces. A lot of traces is actually provided with the repository that we have done. And you can run any of these traces to see how much throughput these kinds of mobility scenarios are actually supporting. So you have the RTE2 agent, and then repository has the EdgeRIC part of the code base as well. So this is what is the entire code base that we are providing right now. Yeah, and in terms of what kind of channel we provide, we've done, right now we have these 4 kind of channel traces available, where we have the SRS UE running on a laptop Then we have a drone. We also have some mobile robots moving around in a room, and we also have the UE on a car. So we have the traces that were collected, these CQI measurements collected from these drive tests, and that we see that is the time evolution of the CQI basically, and we can see how fast the channel is actually changing in mobile scenarios. And that was the main motivation for EdgeRIC to be able to actually react to this underlying wireless channel, to be able to adapt these network decisions to adapt to this changing wireless channel. That was the main most motivation for EdgeRIC. So what are the intelligent decisions we can no, what are the real-time decisions that need intelligence? The resource scheduling is a very important network function. You have MCS selection, that is also something that happens every TTI, and a bunch of other things like interference mitigation, like beam nulling, beam steering, beam forming, also decisions on whether to retransmit or let the packet drop when it comes to latency sensitive applications. And all of this, why is it important? Because we definitely want to, mobility is a big challenge, a well-known challenge in wireless, and with EdgeRIC, we aim to address the problem of this fast-changing wireless environment. Okay, if the build is complete, we can move over to the demo part. It still happened, yeah. With Docker, yes. Yeah. Okay, mine is still building, I'm sure. It's building for everyone right now. Okay, I'm just gonna prepare my other terminals. Okay, I hope everyone's building. Any questions in the meanwhile? Yeah. Here? Oh, these are the applications running underneath. It can be hyper video streaming and so on. The applications which the UE is running. Yeah. Yeah, the network application. Um, Yeah, so the entire code base will be running inside Docker. So for each of the terminal you're in, we have to exec into the Docker that's running.
will just take you to the doctor.
Yeah.
The command is take you.
So this command needs to be run in every terminal.
Yeah.
And
Outside Docker to
yeah, to get inside the Docker. No. Control C and / make run again. Make sure you're inside the Docker before running make run. What?
maybe we can see the
What happened? There is just one container that is running. Oh, yeah, that is a Docker RMI. Yeah, sudo Docker RMI, that container ID. RMI, or you can do star. Star.
See, you want
Star should work. Should work.
how many terminals did you say?
I think around 12. Definitely 10. I have commands for at least terminal 10. All right, my project successfully built. Anyone with a successful build till now? Okay, great. So for people whose project already built, I recommend running these steps inside every terminal. So we need 10 terminals at least for this project. So you can just cd into the code base and then exec into the container by running these two commands. So you can prepare all your terminals by running this command. All right. Who's still building? I'm assuming I can move ahead with starting the network. Yeah, just remember to run this inside every terminal you're running. Just a reminder again. So and ensure that you're inside the Docker before you run any of the commands that we'll run from now on. Yeah, you can ensure you're inside Docker by just, yeah, easy way is this entire line should be in white. Okay, I'm going to start with the other commands running. Okay, we're going to start the GRC broker, that is the GNU radio blocks, to connect our two UEs. We run this command in your first terminal. This is to run the GNU radio blocks. Next, we move ahead to terminal 2, which is to run our EPC file. So, which is your run underscore EPC script should be able to do that. Moving on, we will be running the env /run underscore env command. Should start your network. Okay, you should see this message out here, env started. You know that your network your enode be started. Right after that, we are going to start the UEs. But before you start the UEs, we need to add the UE namespaces into your Docker container. So just run the commands ipnetns add UE1 and add UE2. These are the commands which are right over here. And once you add the UEs, we can start the UEs with this automated script. You can look into the script later, but for the sake of this tutorial, it's all here in the script. So this is a network which basically spins up two UEs that will connect to the SRS RAN network. And after starting the UEs, I'll briefly go over how to change the CQI channel traces. Yeah. You are already inside Docker.
Yeah, but the oh, so the
yeah, you are inside Docker now.
Okay, I gotcha.
Okay, so once make sure that you have an immediate attach of the UEs. You should see the IP address assigned, and which basically means a successful UE attach. So if the UE is attached, you can verify that in your SRS ENB EN terminal, which should be your terminal number 3. You should start seeing these messages on the SRS ENB terminal, which is your terminal number 3. So once you have a UE attached, we can quickly start the traffic. We will CD into the traffic generator folder here, and these are the commands out here. We will start the iperf server. This is starting downlink traffic. So I specified the traffic profile. We'll be running 21 Mbps for one UE and 5 Mbps for the other UE. So this is all part of the command out here. This would be which one? Which one? Can you stop? Yeah, we'll just run the /run SRS UE command, the script. That will start the two UEs. Traffic generation. Yeah. So once you start the traffic, again, you can go back to your ENB terminal. This shows the scheduling masks. Your RNTIs are the UE identifiers, that is RNTI 70 and 71. This is how the RAN identifies the UEs by the radio network, I forgot the name, the temporary ID, RNTI. And this is the allocation mask. We print this every second. Uh, Whatever is the allocation mask, basically the ones means those PRBs are allocated to that particular RNTI. So here basically it means these ones are allocated to RNTI 71, whereas zeros means those are not meant for 71. So ones and zeros are the bit masks, which is basically ones means that particular PRB number one is allocated. Yeah, the PRBs. So once you run traffic, you should be seeing this on the SRS ENB terminal. And the traffic profile we are running is 21 Mbps for one UE and 5 Mbps for the other UE.
So why, they're using the same PRB? Why don't they have the same data rate?
So right now we are just running a default policy, which means everybody gets equal allocations. Yeah. Okay, everybody started with traffic. So once traffic is started, we'll move on to the EdgeRIC part of the code base. I have a different window for running the EdgeRIC side of the code base. Any objections to moving ahead? Otherwise, I'll just move ahead. The terminal number 3, I think. Yeah, the SRS ENB terminal. Wherever you run underscore enb.sh. The terminal number 3, where you run underscore enb.sh. Yeah. Yes, that's right. That's okay. It's just a printing glitch. Yeah. All right. I'm going to start the EdgeRIC part. We cd into the EdgeRIC folder. Oh, yeah. That's a good point. Zero. Yeah. Yeah, just remember to get inside the container, please. Okay. So once you're again inside the container, we'll be looking at the EdgeRIC part of the code base. Moving inside the EdgeRIC directory, we first have to start the Redis server, which is the in-memory Redis database. For EdgeRIC, we start this Redis server here. So you should see something appear on your screen. Then we'll move into the next. All right, we'll start the micro apps now. I hope everyone's with me up until this stage. So first micro app would be, we'll deal with the multiple scheduling policies, including one reinforcement learning based policy that was trained, and the trained model has been provided as part of this code base. So we look into micro app, sorry. First, let's set a default scheduling policy. Let's say we'll first run the max CQI policy. So we are setting the EdgeRIC policy to be max CQI for now. And then we'll start our micro app, which will be delivering scheduling decisions based on the max CQI algorithm. Okay. So you see that the algorithm index is max CQI, and the total system throughput is also being printed out here, which is 14.2. You can see the allocation mask change in this terminal in SRS ENB. Basically, it's trying to allocate 0.9, 90% of the PRBs to the UE, which has a higher CQI. That is, max CQI is known to be the throughput optimal policy, basically, which tries to give always tries to schedule the UE with a good channel. So in an effort to maximize the system throughput. So you can always see that one of the UEs will get 90% of the resources, and the other UE gets only 10% of the resources. So the policy that is running, you can see over there, the algorithm running is max CQI, and the total system throughput that particular algorithm is running. Okay. So if you stop the micro app here, you can see again it will start going back to a default policy, which was again 50% of the PRBs. Yeah. So we are actually running a CQI trace right now. I thought I would go over the trace part after this. Yes. So we provided a separate CQI trace file to each of the UEs based on the mobility scenarios that I described in one of the slides. So if you're not running the micro app, SRS RAN is doing its own scheduling, which is like scheduling exactly 50% of the resources to both UEs. So let's change the scheduling algorithm to say max wait. So this is a buffer based algorithm. Basically, it tries to find like who needs more PRBs, and it allocates a decision based on that. Let's start the micro app for the max wait algorithm. Sorry? It's okay to not stop the previous one also. No, you can update the algorithms like in your third terminal. That's what I did. You just set the algorithm on the Redis database, and the micro app will be delivering decisions according to that.
What was the output that you're supposed to see when you run the terminal 9? I just got it. Okay. Is that correct?
Which was terminal 9?
This was this is what I ran.
Oh yeah. So you basically set this algorithm to max wait. Yeah. It's okay means it's been set. Yeah.
Okay, gotcha.
It should be RL. RL. Yeah. No, it's already part of the code. We have said whether if you choose RL, which model to use is a part of the file. Yeah. So again, if you change it to, if you set it to max CQI, okay, let's set the algorithm to max CQI, and we can again see that total throughput will change, your allocation masks will also change. We can run several other policies like we have support for proportional fare here as well. So you can see the throughputs yield that each of these algorithms are yielding. We see that with proportional fair, our throughput reduced a little bit compared to the previous ones, and your allocation masks are available here. We also support round robin. So we can run round robin, basically schedules each UE one UE every slot. We see that it yields a slightly higher throughput compared to proportional fair. Then we can move to our RL-based model. Let's see. So this is a model. We have already provided the trained model as part of the repository. So if you run the RL model, we can see that it would be using the model which is located in this directory. And again, we see that the throughput increase from the previous one, which was proportional fair or round robin. And so that would be the algorithm running, which algorithm running, and you would have the total system throughput being printed on the terminal on top, and how the allocation masks are changing can be observed on this terminal out here. Yeah. Yeah, I'll go over it. Yeah. So if this works for everyone, I can go over okay, before I move over to how we did the training, let's just see like what are the messages basically looking like the RTE2 report. So if you go into MuApp3, the folder for MuApp3, it's basically a monitoring micro app. So, and if we run this MuApp3 underscore monitor underscore terminal.py, we can see the metrics received and the scheduling policies. So if you look over here, we have the UE dictionary, which is sending the RNTI and the metrics associated with the RNTI. And then you have, this is 70, and then you have the metrics associated with 71 somewhere around. Yeah, 71 starts over here. This is the UE dictionary being sent along with the RAN index and the RIC index. So this is our RTE2 report. Similarly, the RTE2 policy is basically saying we received that this is the action for this particular TTI, which is the TTI just before one. So EdgeRIC basically runs one TTI behind basically. So this is the current TTI received, and we are sending the action for the previous TTI. So yeah, and this is the scheduling weights. That is 70 should get 1.7 and 71 should get negative, which is kind of normalized in the SRS RAN code base. So this is what so you can keep monitoring the messages being sent to and fro between RAN and RIC. Similarly, if you set it to say max CQI now, you will always see the weights being sent is like 0.9 and 0.1. The scheduling policy now becomes 90% and 10% here. Okay. Now, if nobody has a question, I will kind of move ahead and show how to basically train on. Yeah. Um, Printing has a glitch. Sometimes you will not see things.
I can see sometimes we don't have any scheduling.
Oh, no. It's just a printing glitch. There will be scheduling every TTI. So how do we train on our platform? We leverage the OpenAI code base and we use the gymnasium environment. which accounts you to run any kind of feedback based algorithms, that is to receive a state and send back an action corresponding to that particular state. Um, okay, so you have the environment here. Our environment is basically the radio access network, which will send the states. If we want to integrate any kind of application awareness into the network, that also becomes a part of the state, which is sent to EdgeRIC, which has this OpenAI Gymnasium interface, which is running an RL agent there as part of micro app. Micro app number 2 in this code base is a reinforcement learning training agent, which is it receives states every 5,000, receives 5,000 TTIs worth of state, does back propagation, and it kinds of continuously learns. It takes like 30 to 40 iterations to train. And once the training is complete, it's converged, we kind of put it in the particular folder inside EdgeRIC to run that particular inference policy in real time. So yeah.
So the training over there, how much of processing do you need?
So we are running everything this natively on CPUs. So it is very important that you actually customize the model to be a very small network that actually that can actually do some computing. Here it's basically a 64 cross 64 neural network. It's very small. Yeah, and we are using an off-the-shelf reinforcement learning policy, which is the proximal policy optimization, which is PPO, and it seems to train fairly well in this environment. Uh, in terms of the network state, what we did here, sorry. Okay. Okay, so in terms of the network state, the way we are training this agent is basically we are pulling the CQI and the downlink backlog buffer. That is my state space for this particular reinforcement learning agent, and it is sending the scheduling weights back. The specifications is your state space is basically the CQI of each UE, the backlog buffer of each UE, which is BI, and CQI is the CQI part. The action is basically the weight for each UE, and how are we training it? The reward space is basically the total system throughput. So this agent that we trained was with the objective of throughput maximization. So you could see that our reinforcement learning had always the best. The RL agent always gave like the higher system throughput as opposed to the other policies. Yeah. 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 So this policy training is offline. Yeah. So we train it completely in this GNU radio block kind of environment that we are doing right now. We take the model, put it into EdgeRIC, and we can do over-the-air experiments and show that that particular trained model on this environment gave much better results. We have some demo videos available for that, with running over-the-air experiments with reinforcement learning trained offline in this way is giving like. Mm-hmm. When you say big state space, so right now the input size is basically 2 metrics per UE, so it would be like n UEs into 2. Yeah. So when you have 200 UEs, that's where I said we need to look at model customization. So we've been looking into approaches of compressed sensing as well, where you want to not look at every 200 UEs every TTI. If you know that I schedule like 5 UEs in the last 5 TTIs, I will definitely not compute a policy for that in the next TTI. Yeah. Yeah, so there is a lot of ML research as well if we actually want to deliver this real-time control to the radio access network. Yeah. Mm-hmm. It can. The work we did with OAIC is actually a multi-site environment. We had 2 EdgeRICs at the 2 sites. Yeah. So. Mm-hmm. EdgeRIC is not designed to communicate at all with the core network. It just talks to the DU as such. It can talk to the cloud-based RICs through some interface we haven't decided. Mm-hmm. Updated model to EdgeRIC. We haven't decided. It could be any interface to where the cloud-based RICs talk to EdgeRIC. No standardized interface as of now. Okay. So now I can go over where you can find the training code base. So if you look into the EdgeRIC portion of our code base inside MuApp 2, this is the file which has our entire training pipeline, and everything here. Um, Yeah, the stream_RL is basically the folder which contains all the libraries to actually deploy the reinforcement learning training. So it's worthwhile to look into this particular folder. Now, where do we store the models? And inside MuApp 1, we have a folder called RL model, and we have these models trained in this folder. This is a fully trained model, this is a half trained model, and this is like a starting model. So these are already trained models that is provided as part of the code base. And if you want to go ahead and train your own policy, you look at MuApp 2 and you can look at this particular file and you can update your reward, state, and action. Where do you upload? Stream_RL is the one which has the environment specified. We have an environment called the EdgeRIC.py, which does the state update to get the next action. Similarly, we have the registry. Yeah, I think so there is this file called rewards.py. So you can change your the objective reward based on this file. Like we also trained another agent for a video streaming kind of a use case where our objective was to maximize video streaming experience by reducing the stall duration. For the demo here, we show that we trained with throughput maximization. So this is the file where you can set your own rewards, what you want to maximize through your RL agent. Yeah, so basically this folder contains your entire, all the libraries needed for training. So your MuApp 2 is basically a training MuApp, and MuApp 1 is the one which uses a trained model to actually infer in real time and give the decisions to the radio access network. Coming back to the channel traces part, which I talked about, where we find the CQI files. In the SRS-RAN UE code base, we have these two files called params1.txt. This is where you kind of specify the CQI trace file that was collected from various experiments. All the trace files are located in this folder. These are multiple trace files. I think they are correctly named, like the duration, like when you say CQI car 10 mph 3 minutes, it's basically a 3-minute run with a car running at 10 miles per hour. These are the trace files which is available in this folder. You can simply replace the trace file here with any trace that you want and rerun the network to see what performance you are getting with that particular trace. This is the CQI part. Yeah, I think that's about it that I wanted to talk in the demo. But we have a couple of more interesting new apps that I can talk about if no one has any objection. Or do you want me to go over anything from the code? Yes.
Why are there, so in this one right here, what is with the, I guess, gaps in the allocation mask? Is that just like a buffering thing, or?
It's just a printing glitch.
Oh, okay.
Yeah. If you actually do it in a log file, you can see all of them.
Okay.
Yeah, yeah. Okay. Yeah, then I guess I'll go over some other mu apps that we, yeah. Sorry. Um, any questions, anything we would want to look at in the demo?
Were you all able to run this? So this is just a monolithic deployment.
Yeah.
Right? So did you try this with like a CUD split?
We'll release the SRS RAN 5G version, I guess, in a month or so. Yeah. So that's the one which will come up with the CUDO split. So this is all on SRS RAN 4G, which is the monolithic stack all in one process. Okay, I think we've deployed a couple of other micro apps and we can briefly go over that. This is a video scheduling micro app. We just wanted to see what happens if we actually integrate some kind of application awareness in the scheduling decisions. We deployed two UEs which were running a video streaming application and another very high throughput application running in the background. So the way we trained this agent was with the objective to minimize the stall duration. That is, every time the media buffers of the video streaming UEs went down, we gave it a very high negative reward, like -20, like -20. So it basically, the agent tried to schedule the resources to the UEs which are always starving of the playback media buffer. So that's the media buffer. So we incorporated the third state into the state space of our RL agent, which is now the network states, which is the backlog buffer, the CQI, and now we also have an application state, which is the playout media buffer of the video streaming client. The action space is remain the same, which was the weights to be allocated to each UE. And the important change was how we did the reward. Here we just trained the agent, like heavily punishing it whenever the media buffers fell below the threshold in which it will actually start rebuffering. So you have micro app, we get the CQI and backlog buffer, and we ask EdgeRIC to communicate directly with the app server in this case to pull out the media buffer state. So this is, sorry. So this link is a real-time link, but this link is a little bit delayed, which has like a 30 millisecond delay. But even this works pretty well when it comes to actually seeing the training and the actual results. So this part, sorry. So again, EdgeRIC sends the scheduling weights based on both the network and the application state. And what we see is that for an application agnostic scheduler, which is like a max weight or a max CQI scheduler, which just sits in the RAN stack without any idea about what applications is going on underneath, we see that in bad channel conditions, the media buffer often falls below the minimum threshold, which is why it leads to like rebuffering events. Whereas when you have EdgeRIC, it is in cases when the media buffer actually falls below the threshold, it can quickly recover to maintain that 2 second worth of media, and thus reducing the stall time significantly. So so basically, we wanted to claim that even by integrating this application aware decisions into the RAN functionalities is kind of pretty beneficial. This was a project done in collaboration with the OAIC team. Yeah.
So is there a best solution for which
So we did it across RL agents without application awareness, with application awareness, as well as all the instack schedulers without application awareness. The one which was trained to actually, which was trained with a very high negative reward for rebuffering, actually gave the least stall duration or least rebuffering time. Does that answer your question?
Sorry, like you mean the real RL schedule is?
Yeah. Okay. This was, yeah, this is a multi-site resource allocation project. Um, yeah, yeah. So we are looking actually inside a slice. We are not even looking so high up in the layers. Once you are inside the slice, we are looking at the scheduling algorithm that is happening in real time. Yeah, yeah. So this entire thing that we are running can be considered to be running all inside one slice. Yeah, yeah, we are looking into it. Um, so this was how a scheduling across multiple sites work in conjunction with the ICX app that we saw today morning, where the ICX app was responsible for interference detection to understand the kind of intersite interference that exists across multiple sites, and EdgeRIC is responsible to actually distribute this limited spectrum across the three sites based on the background interference. So this was a very interesting use case where a near real time actually augments real time RICs to actually deliver enhanced system performance. Where situational awareness, basically awareness about the spectrum, comes from this ICX app, and the real time resource distribution across the sites uh, comes is a decision of the real time RIC. System benefits, yeah, we have like some, you see a much higher SNR because you are avoiding the interference. Basically, EdgeRIC avoids the PRBs which are interfered with. Then, as a result of that, by eliminating interference, you're reducing the number of packet drops, which ultimately leads to a much higher system throughput. I think I'll give it over to Ish. Or
Any questions so far? One question we had, how many users are you attaching?
right now it's 2, but it's due to system capabilities, we have only done 4 proper users, and the algorithm efficiency was shown with like 50 users in simulation. No.
So right now we are not dealing with mobility and handover yet, but
We are just dealing with one single site.
future, basically, the way you can think about it is EdgeRIC provides a hook into the RAN where you want to control certain policies. Here, the policy that we have so far talked about is the scheduler, where you can produce certain weightage to different flows to um, like create a new scheduling policy based on RN and whatnot. Next, we'll talk about some of other hooks which are placed into MIMO beamforming related to security and some other areas. And if you want to do, let's say, efficient handovers, then we can identify appropriate places in the SRS RAN code where these handover decisions are being made, and then we can provide a hook to have a control message going to the schedule, the handover algorithm, and then you can create an X app, or in this case micro app, to do handover. So this is a generic framework, and we are keep on expanding and looking into new application scenarios. And that's exactly I'm going to talk about one of the next application of EdgeRIC in the MIMO. Before there, any questions with the scheduler?
In general, can you use EdgeRIC to control multiple base stations?
Not really, not multiple base stations. Multiple RUs, yes, but EdgeRIC is co-located with the DU. So we haven't looked into multi-DU coordination with EdgeRIC. But
So you assume that each DU is like an edge,
yeah.
right? And it has an edge server.
Mm-hmm.
Yeah, this is a separate server.
EdgeRIC? No, it is supposed to be co-located because you need the inter-process communication to actually reduce the latency. And the yeah, Not separate hardware. The idea is to have it co-located. Basically, we want to use the same compute because the inter-process communication latency is the main bottleneck for real-timeness. It could be, we right now we are doing ZMQ. We are also looking into shared memory approaches.
So the way we are looking at micro apps is not like how we look at XApp or RF. There you are running in baseband unit or a separate controller, and they could be deployed by different vendors. But here it is very tightly integrated. Otherwise, you won't get microsecond latency. But it is a platform to allow building applications, even though it is integrated because we have a Python based controller, which where like EdgeRIC controller, where you can run these different applications, and they can run at their own time scale while getting data from the RAN in microsecond with microsecond latency.
So what kind of hardware do you have in this question? So take the implementation of the rig, the PU and everything. How big is it? What type of hardware you have in there?
So we are running.
All of this is in CPU right now. All of this is just CPU right now.
Everything is running on a.
Okay, this is everything CPU right now.
Sorry, I forgot.
Yeah.
2 days during the day. My fault.
Yeah.
But do you have any estimate how? It's really good work. The thing here is, as you said, everything is coupled. It has to be able to run in as small as say the edge, because in the edge you don't have a lot of computing there. But it'd be interesting to see how much power does it need.
So with all our current evaluations, we did some benchmarking. With running all of this RL and so on, we like running almost like 4 or 6 UEs, we saw a 10% increase in CPU utilization when we are running the RAN with and without EdgeRIC. Yeah. So I think SRS RAN is a very lightweight software. It actually uses only 5% of the total CPU that's available. So So EdgeRIC, that's why we talked about the TTI by TTI synchronization. If we cannot deliver action, we don't do anything.
So the XApp is not blocking the RAN. RAN is working with its own thread, its own timeline, and the XApp is running on a parallel thread. Let's say if the XApp is running some extremely heavy compute like reinforcement learning or some advanced machine learning is taking a lot of time, and you're not able to meet the microsecond deadline, then let's say you're doing it 5 milliseconds or later. That means the RAN will keep on running with the last used policy. It will only update when it receives a new policy from the XApp.
Yeah, so TTI bit by TTI sync is the most important part of any real-time control because you have to act on the state that was actually received. Otherwise, if you break the state action correlation, I think everything will fall apart.
Okay, so for the next maybe 5-10 minutes, we will talk about a couple of other applications that we use our platform to build. So far, Ushashi has talked about the scheduling application, multi-base station coordination. That means a couple of work that we have published in NSTI, SIGCOMM, and under submission in Codex. Next, I will talk about a bit on security and privacy. We have built a Beam Armor. It's an app which runs on EdgeRIC to provide MIMO capabilities into the RAN. And using MIMO, the first application we built is how to do I think it's defined.
Okay.
How to do anti-jamming. When there is a jammer, MIMO provides a way to create beam learning and manage different directions. Next, I will go through one of our more recent work which are ongoing in energy optimization and running AI-driven application where I will So what is beam armor? Right? You have a base station which has multiple antennas, let's say SRS, EMB. You have attached to the user. We are running uplink transmission, and then EdgeRIC controller provides us an app. We call it beam armor app to monitor the wireless conditions in a MIMO environment and control the base station. Let's say we have a jammer. It will create a jamming signal towards the base station, and it will affect the overall uplink throughput. What we can do is using multiple antennas at the base station, you can create a shape of a beam which will null the direction of the jammer. Okay, this is a very simple XR we want to create. Let's say. So what are the requirements? This jammer need not be actually a malicious device. It could be a nearby base station, which is creating interference to the other base station if they're operating in the same band. So the overall architecture that we have built is we have EdgeRIC controller, which is running beam armor app. On one hand, it has control over ORAN, and on the other side, we have our application. From the ORAN, we need a couple of KPI metrics that EdgeRIC provides. It provides us the RAN configuration, the state of RAN. It provides us access to MIMO channel, which is some additional functionality that we have built for this application. It provides all the KPIs like SINR, blur, and throughput, which we can use to understand and monitor for the interferer, whether there is interferer or not, so that we can take appropriate action. Once we are running the app, it has all the data. It can create a beam nulling vector, and then it can feed that beam nulling vector back to the RAN as a control policy message, and the RAN will implement that beamforming vector. We can use it for a couple of other applications related to MIMO, like MIMO user selection, MIMO beamforming, and antenna selection, even sensing applications like localization and tracking, because MIMO channel can give you all this information. So this beam armor app is also open source. It is now part integrated with EdgeRIC. At that time, it was a separate repo on itself. If you are interested in just beam armor, you can also look into this GitHub repo for the code piece. So as basically we have all seen how to run this beam armor app. It's very simple. If we run it with EdgeRIC, it is a Python interface which has one line of command to get all the data into your Python from the RAN, and you create a policy that is the code that you can write yourself, and then you can send the policy vector. We call the policy alpha. You can send the policy alpha back to the RAN. The very simple implementation we did for the policy is we implemented this a year ago when we were still working with SRS RAN 4G, and SRS RAN 4G only allows 2 antennas. So with 2 antennas, we don't have much capability. What we can do is you can think of this like a shape of a beam which has high energy towards the jammer. You can reshape it or rotate it so that you create a null towards the jammer. And it is possible with 2 antennas, and we demonstrated it by creating a beam nulling vector which can create a null towards the jammer. How we implement it? We have the SRS RAN which sends upstream data Y1, Y2, which is the data received from 2 antennas. Here we implemented with raw IQ samples. So we collected an IQ sample from each of the 2 antennas, which is Y1, Y2. Our controller creates the beam nulling vector. We call it alpha vector. And then this alpha vector you can apply at the RAN such that you take a linear combination of Y1 plus alpha by 2, normalize it so that the power is normalized. And this very simple application of beam nulling will create the appropriate null in the direction that we estimate at the controller from Y1, Y2. Yeah.
So the job in this scenario is like constant reactive. What type of job?
So we consider a jammer which is continuously streaming some random data in the band of your interest. So it is basically jamming everything. It is not a selective jammer. It will disrupt the entire uplink communication, both control and data.
So what type of signal does it transmit?
It's a random OFDM data, for example. So we considered multiple jammer. We considered one jammer which is a single tone. It's just transmitting a tone in one of the band of interest. We considered wideband jammer, which is transmitting some random OFDM data across wide subcarriers. And we basically use a standard SDR like USRP to create some random forward beam signal and tone. Okay, so this is our setup in lab for the beam armor. You can see we have all the SRS RAN is running on the server up there. These are the antennas. 4 antennas are used for the base station, 2 for transmit, 2 for receive, and then we have one user, and then we have one jammer on the other side. And if we don't have jammer, then you can see we are getting continuously high SINR of like 15 dB, and the blur is almost 0 as as desired. But as we turn on the jammer, you can see the SINR goes down to 0, and the bit error rate goes high 50%, which is the worst bit error rate we can get. Now, if we turn on our beam armor app, even though you can see that without beam armor, our SINR has gone down to 0, we can recover it back to the green line. Green line was the baseline without any jammer. So running this nulling is so effective that we are able to recover back the original SINR. We're able to recover the original throughput level, and the blur goes down very close to 0. So in a way, it shows that a very simple nulling with only 2 antennas, by estimating the jammer channel, we are able to null towards the jammer, and it shows a good real-world demonstration. We have a video to show basically how the entire setup is working end-to-end in real time. So we'll go through. So here you can see this is our setup with the base station, user, and jammer in our lab environment. The base station is running the SRS RAN front end with USRP X300 in a particular uplink and downlink frequency. Here we are interested mostly in uplink. This is the user setup. It's running SRS RAN UE in the same frequency and 10 megahertz of bandwidth. This was our jammer setup. We used a simple Bluetooth SDR, which is much more lightweight to create jamming. And jammer has a bandwidth of 5 megahertz. Alpha 1, alpha 2 is the alpha vector that will create null towards the jamming direction. So in this demo, we are showing time series of blur, SINR, and throughput. When nulling is not applied, we can see the SINR is very low, and then we will turn on null by just turning a switch, and then you can see the SINR goes up, the blur starts to go down, and the jump in throughput is also visible. So overall, this was a live setup, and we were seeing around 10 dB increase in SINR and up to 2 times increase in throughput. Okay. Any questions from my end?
Again, as a new app, I mean,
yeah, we implemented with EdgeRIC, so it has a similar interface using GMQ. So the structure is similar. In terms of latency, are we able to achieve microsecond or millisecond level latency here? The answer is no, because the amount of data that we need to send to the controller is high. Here, when we are working on it at SRS and 4G, it doesn't allow us to estimate channels and send it. Like in fact, MIMO in uplink was not even implemented. It is now implemented in 5G, and so the new version of beam armor 5G, which is under we are still working on it, that allows us to estimate the uplink channel directly and send it to the controller. Here, since we are streaming raw IQ data, we had to downsample the data because it's a huge amount of data to send in a limited time. So with that, we reduced the timeline, but it still works because we are not bounded by the XApp to run fast. So in this case, if the jammer doesn't change its location or if it is not moving fast enough, then it is okay to update the beam nulling vector only once in a while. Yeah, both. So we are using IP sample for detecting whether there is jammer, creating and estimating the alpha from there using the relative phase across 2 antennas, and then we are applying that alpha in real time to the LAN. It's just two antennas, so we just use simple matching network. Yeah, so we use a simple least square problem. It's a simple operation problem to detect.
See, the thing, this is very interesting, your work. The thing is, when you say you want to put a mall,
Yeah.
but in real life, you will never hit a mall in there. So you'll be able to fall either way. And I'm just wondering, you're going to be into an oscillation state, you're in and out and everything. That's why implementing in less than 1 millisecond is very important.
Yeah, so in the next version, when we are working with SR7 5G, we are able to meet the 1 millisecond timeline because the amount of data that we need to send if you are sending the only the channel estimates, then it is quite low compared to sending the entire IP sample.
But you're assuming that the jammer is in the mall. Perfect.
That's the performance. Like theoretically, the null is very sharp and it can create like extremely high nulling, like around 30-40 dB null can be achieved. But practically, it depends on the accuracy of the estimation algorithm.
Yeah.
So if the algorithms are not accurate, they're not able to estimate the angle of the jammer very accurately, then it will suffer from some of the degradation. But we have demonstrated that, like, our algorithm is accurate and it can do very sharp numbers. One of the issues that we are right now utilizing or looking into is multipath, because we don't want to just null in one direction, but if there is a lot of multipath, then you want to create null in multiple other directions. And we cannot do it with just two antennas. We need more antennas to do it. And so in the latest 5G version, we are doing multipath aware nulling, which take care of using 4 antennas and across multiple frequency subcarriers to create null for each frequency subcarrier separately, rather than creating a single null for all frequencies. Okay. So the other work on energy optimization are still ongoing. I'll maybe talk about very closely in one slide what we are doing. So first step is we are first monitoring what are the most energy consumption part in the network. The whole idea here we have is how can we reduce the energy of our phone, because that's the most important part. Like for the base station, we have a lot of energy available. That's also we are looking at. But what we can do in the network protocol side, so that we can reduce the energy consumption in the phone. So we did some of the measurement study. In the chart, we are showing how much is the power consumed in our cell phone with different applications. We use one of the tool released by Google to do power measurement in a commercial phone, in a Pixel phone, and you can see when when the phone is standby, then almost all the applications like display and cellular are the most power consuming part. They are consuming almost equal power. But as we turn on certain applications which are more network heavy and compute heavy, for example, the last video call, then you can see the cellular part, which is in blue, starts to consume more than half of the power. In fact, much more than the power consumed by display or compute. The compute in orange and the display in red. So basically, this motivates to build new solutions to ensure that while we are streaming our 5G data and running the 5G cellular service on the phone, we should be energy aware, and we have to design a protocol to reduce this energy consumption. The other work that we are working on is application aware networking. So here we want to build with EdgeRIC our XApp or micro app, which are aware of the end-to-end application state. For example, you are streaming a video. The state of the video could be your playback buffer, your latency, your status of like what kind of video encoding you are using. So a couple of these things, if we know at the network level, then we can do cross-layer optimization. The file layer, MAC layer, and the application layer, they will work together to create and to come up with a good network decisions, such as allocating resources to the user traffic and scheduling in a much better way. But currently, there is no existing framework which can do application-aware networking. Like the base station doesn't know how the end-to-end video buffer is created, because that is only known by the end-to-end application, like either at the server or at the user device. So we are basically creating a loop where we have two parts. One is the user app, which is running on your phone. Okay, so your phone has all the knowledge about the video information, what is the playback buffer, and so on. So we take this information from the user. The user also knows is a user identifier, user ID, so that we can associate the application state with the user ID. And once we have associated it, this information goes all the way to our XApp or the controller, and this controller matches the user ID with the list of user IDs which are connected to the base station, and then it applies the policies to that user ID. So in this way, we close the loop. We have the controller which has now some external information about the user flow, about the application. So this is only possible with a controller kind of environment where this controller can run at its own timeline, and it can use additional information which is not available locally at the base station from the user, from external sources, to build better networking solutions, application aware solutions. So this is the bigger picture what we are working right now, and we believe that it will solve one of the important problems in video streaming and a couple of these heavy applications, solving for power and solving for building machine learning and reinforcement learning based solutions in this end-to-end framework.
Can you explain what's the line between the controller and the RAM?
Between the controller and the RAM?
Yeah, the bi-direction.
Yeah, so that is exactly EdgeRIC. So it on one side from the network we are getting the KPIs and a couple of information from the RAM to the controller, and on the other side we are giving network decisions. So network decision could be in the form of scheduling decision, it could be in the form of network slicing decision. So it is basically how XApp works. Like on one side you get information from the network, and on the other side you can create policies and send it back to the network.
So the decision sending to the app or the sending to the RAM?
So this is the app. The green part is the app, and blue is the RAM.
Yeah, but the decision, the app decision, and the RAM decision are two different decisions.
Yes. So the app. So the part which I didn't talk about is now the app also has the capability to influence some application decisions which can affect the server. So if we want to, let's say, inform the web server to change some of the end-to-end application states, then we can also control that. So the interesting part here is that the XApp, which is running in the controller, is not only having access to network states and network decisions, but now it has access to user application states, and also has a way to influence some application decision back at the server. It could be your video server at one of the edge compute, or it could be somewhere far. So as long as you have access. And so now basically the building XApp is not only done by network engineers. Now the end-to-end application providers can also come and build their own app, so that they can control their app states as well as network states.
Can add to that, like cloud gaming and applications like that, they suffer from heavy packet losses, which just makes the game very hard to actually make it happen. And adaptive bitrate has been a long-standing problem in video streaming, especially over wireless, because of the unpredictable nature. So by having this controller, having the raw access to the raw network state, you can actually give the exact decision to the app server, so that all these estimation-based algorithms then can become much more accurate in deciding the bit rate or the frame rate or the encoding, the compression, and a lot of other things which today is done by estimation-based algorithms like ECC, UW. They run their own estimation-based stuff. Right now, we are saying we'll give the raw stuff.
So the developer needs to specify whether they want to connect to the what they, what actions they need to be able to assess this.
So what we are imagining is the controller opens up a server which anyone can look into and connect with it and create create a bi-directional link, right? So that this need not be a real-time link, or it could be real-time link. It could use a standard TCP/IP parallel interface. So how exactly these links are created, that's depends on the way of implementation. But what we are the way we are thinking to implement it is just to create a separate parallel interface to connect the two. So it could be a standard TCP/IP interface to connect the two. Okay. Yes, we can.
Once you were talking about cross-layer optimization and the machine learning at the same time. First of all, I know that how do you share these data for training and learning in the app? And is it centralized or not? Because we were talking about the network.
So the question first you are asking, how are we collecting data, right? So
Feedback. Feedback.
yeah. So it's the we are basically running the network. We are running an application with the application server, and at the same time, at the controller, we are saving two kind of data. One which is network states, and other which is application states. So because from the user side, we have the access to the user states or the application states that are running for the video streaming. We are logging that data. And for the network side, we have the data for the network states in terms of the scheduling decisions that are being made. So that's the data part. And once we have the data set, then the algorithms that we will be designing.
Basically, like reinforcement learning is learned by doing. That's the good part about reinforcement learning. You don't need data.
No, I want to know that when you are training, so like the estimation and said.
So you leave your entire scenario to run. The agent just runs random stuff in the environment. It keeps collecting its own data by taking a weird set of actions, and then it finally converges to a policy, which it thinks is optimal.
Sorry, you cannot if you actually add in the real network to train because if it is not trained, so the action is not acceptable. You have some consequences. You should actually have a bunch of data to train it offline, and then use the training maybe when not getting.
So you start off the training in a ZMQ-based network where you know very clean data is coming for your initial starting part of the network. The agent converges suboptimally, then you go to the real world so that it can quickly adapt.
Yeah. So we have GMQ-based distributed environment where we can we
leave it to run for hours and hours. It learns something there, then it moves to the real world and adapts.
Yeah, if it has your metrics.
So yeah, the way we have been implemented this is we collect over the air CQI data, we log it, and then we replay that CQI with GMQ-based interface so that it can just run on those network traces with the different settings, with different network states that it is learning on the way. And then once we have a trained network, we can deploy it in a real world. And at that time, because it is reinforcement learning based, it will keep on learning and it will keep on training while it is being deployed.
So that is kind of like centralized.
By centralized, do you mean it is being located at one of the
because even though each agent is going to be optimized based on the parameter that you define in the network, so they need to share to each other at the point that they want to get to that specific target.
So right now there is only one
you just
controller.
have one agent with
One
one objective to maximize.
Yeah. So probably when we expand into multiple applications, we might have go into that issue. But at this point, we have a single agent, single controller. Yeah. So yeah. Thank you, everyone.
Thank you.